Hi students, I am Deependra Sharma. I am currently working as a research scholar in physics department at IIT Bombay. So in this video I am here to tell you that today is the birthday of the Ramanujan. He was a very good mathematician, and I was thinking from some last days that why should not I prepare some lecture series on mathematical physics. So today I thought that this is the best time to start. I have a book on mathematical physics by the retired professor V. Balakrishnan from IIT Madras. He wrote this very book. He wrote this very good book, and this book is for the research students in the science and engineering field, both fields. And I went through all those chapters of this book, and I found this is a very rigorous and good book. So I will be preparing lecture on the 32 chapters of this book, and will be dividing each chapter into the two to three parts, and each video content will be of the 45-minute duration. So since this is a introductory lecture, so it may be that it is a 20 or 30-minute lecture. So the first lecture is on the function of real variable. So in this video, we will learn how to plot some function of real variable and some integer or fractional power of the one-dimensional real variables. Okay, so if you want to know more, please see the further videos. Okay, so to plot some basic graphs, we have 7 to 8 points. We should look for them, and if we correctly find and satisfy with those points, and we will be able to plot any difficult graph. Okay, so it is not necessary that you have to look for all those points which I am going to tell here. Uh, a less number of those points will also be you will be able to plot if it is a simple graph. So let us look what are those points which we should look for. Number one point is what are the zeros of the function, means what is the root of the functions. So we should look it for. Number two, maxima and minima. So basically, finding maxima and minima is finding the first and second derivative, right? Number three, inflection point. This is the point where the function changes its curvature. Okay. Number 4 point. So it is not necessary that you need all these points. A subset of these points will also be sufficient if it is a simple graph. It is some technical function, then you have to go through all the points. You may have to go through all the points, right? Asymptotes. I will tell what is asymptotes in after some few times. Number 5, discontinuities. Number 6, infinities and divergence. And number 7 is behavior of the function near behavior x near a small value of arguments. So if function is a real variable function and it is one dimension, so you will say that a small value of other argument will be, for example, a function of x, where x is a real variable. Then you will say you will look for the function behavior near x equal to 0. So that is the meaning of this point, right? 8 number point, the behavior for the large value of argument. Same thing for large value of argument. So for example, if the function is f of x, then that is x tends to in plus minus infinity. So you have to find the behavior of f of x at x tends to plus minus infinity. So these are the things which you should look for. Then you will be able to plot any graph. So let us look. So first thing, I will be plotting the simple graph, the power of x, right? Suppose we have one dimensional function, a real variable function f of x, which is some power of x. So first point here, I'm going to take some power of x. Fine. So what you can take? Suppose f of x equals to simply x. So this is a linear plot. You can, so here you don't need to go all those 3 points which I told you above. Here you can easily see that this is a linear plot. If you want to go all those points, you may go through them, but it is not necessary at each function you are going to plot. So it is straightforward, that is a linear graph. So if we plot it, how it will look, let us see. So the plot will be like f of x will be like this. Fine. So this is f of x, this is x, and this is f of x equals to x. If we want to plot f of x equals to x square, then how it will look like? So it will look like, it will become a little bit flatter at x tends to 0, and at exact x equals to 0 it will be exactly flat. So it will look like this, and it will also pass from the point 1 comma 1. So it will like this. So I'm just plotting the function in the first quadrant, so that the figure does not become very cumbersome. Number 3, f of x is equal to x to the power 3. So how it will look like? This will become more flatter at x tends to 0 and more steeper at x 1 comma 1. So it will become like this. So the first one, this is x square plot and this is x cube. Fine. So if you want to check above those points, let us check some few points which I told you are above. Let us investigate those points, whether I'm doing correctly or not. So let us find the first. What is the first point? First point is find the zeros. So these three functions, all these three functions have zeros at x equals to 0. Means they pass through the origin. Yes, they are passing. The second point is, what is second point? The second point is maxima and minima. Since the first function, this function, it has the first derivative, and its first derivative is 1. So its slope is 1. Means, means it makes 45 degree everywhere. Its slope is constant through all. So its slope is constant. F of x, if you take the derivative of f of x, which this with this for this function, this comes to be 1, and it is constant everywhere. This slope is not changing. So this means that it has no maxima, no minima. Okay. If you take this function f of x equals to x square, if you find the zeros, you will find one zeros, and that zero is origin. Means zeros means the root of the function. And if you try to find the first derivative, means the slope of this function, let us do that. That will be 2x. If you take the derivative of this, so its slope is not constant, it is changing linearly. Okay. So this means that if the slope is changing, there would be somewhere some maxima or minima. Let us check whether it has or not. So 2x equals to 0. Sorry, this is the slope f prime of x. This is slope. So how would you check the maxima minima? So what you will do, you will just equate it to the 0. So f prime of x at x naught, where the maxima or minima exist, 2x naught equals to 0. This means x is not equals to 0. So this is the point of maxima or minima, right? If you want to check whether it is maxima or minima, we will take the second derivative. So f double prime of x will be just 2, which is constant, right? So, and it is positive. So when the second derivative is positive, this means that the function make minima. So at x equals to 0, it will make minima. So that's why if you extend this x square function in the, so this is x square. So you can see here that it is making minima at x equals to 0. Fine. Similarly, you can check for x cube. It will also have only one minima. No. Whether it has minima or not, let us check. So f of x equals to x cube. First derivative is this at x naught for to check the maxima or minima. X naught equals to 0. This means x naught square equals to 0. So we have one point where the first derivative is becoming 0, which is 0. Let us check the second derivative. So 3 times 2x, this is the second derivative, and x naught, it should be, so this is the second derivative at x naught, and this is the first derivative. So if we want to check second derivative at x naught and x naught equals to 0, the second derivative is also coming to the 0. This means that when the slope becomes 0, it means that function become flat at that point. But when second derivative is 0, this means that it is not making any maxima or minima. If it is positive, then it is minima. If it is negative, then it is maximum. But here we see that in case of f of x equals to x cube is not making maxima or minima, while it is making some inflection point. Let us check whether it is that now. So this is x cube graph, and if you check, this graph will go like this. So this is origin point 0, 0, and this is the inflection point where the curvature of the function is changing. So first the the sign of the curvature is changing. So what is the definition of the curvature? What is the definition of the um, curvature? Inflection point. So the definition of the inflection point is that point where the function changes the sign of the curvature. So first, so curvature rate. So you have, if you don't know what is curvature, so always curvature lie. So curvature. So for a case, let us consider a circle. This is circle, right? So this is a curve. Okay, this is curve and it is these are the radius. So this, so if for the simplicity I'm just telling you here, but it is a many more in detail. So this is a circle and this is its center and this is curve. So its radius of curvature lie at the center. Okay. So here for the case of f of x cube, you may guess for the case of this part, the lower part which is in the fourth quadrant, this is the fourth quadrant. In this quadrant, where the center of this curvature would lie, somewhere here in this region. Okay, in this region somewhere. And for the above part which is in the first quadrant, the curvature radius of curvature, the point of curvature would lie somewhere here. Okay, so radius of curvature here, the radius of curvature would like this. Here would be the radius of curvature would like this. So like in case of circle, the radius of curvature will for this curve is like this, which is passing through this center. So for the lower part of the curve, the radius of curvature to is directed towards downward towards this, and for the above part of the curve, the radius of curvature is directed towards above. So sign of the curvature is changed. That's why this is the point of inflection. Which is the point of inflection? This origin. Okay, so it does not have, it has the flat point at x equals to 0, but it is not a maximum or minima. Fine. Okay, good. So till now I taught how to plot some power of x. Now we will check how to plot some fractional power of x, right? So with these points, 8 points, if you find all this, if you go through all these 8 points, you will be able to plot any simple or difficult graph. So let us look how the fractional power of x will look like. So let me plot on over this. Let me plot with the blue color. So if you plot x to the power, so integer power function are flatter at x equals to 0 and are more steeper at 1 comma 1. While when you plot some fractional power, you will see that those function will be more steeper at x equals to 0 and will become and will become and will become more flatter at 1 comma 1. So if you want to see, x to the power half will look like this graph. This is x to the power half. This is x to the power. This one is x to the power 1 by 3. So as you increase the power, shape moves away from the straight line. So if the integer power 1 is separating the two families of curve, and x to the power 1 is the separation line between the two families of curve. One is integer family curves and one is fractional power curve. So if you see x to the power 1 by 2, x to the power 1 by 3 will be above the straight line in the first quadrant, and the integer power of this x, those function will lie below the this straight line, right? So this straight line is the separation between these two families of curve. And one more thing I want to repeat again, that integer power are more steeper at 1 comma 1 and flatter near x equals to 0, while the case is reversed for the case of fractional power. Get you point? Okay, fine. Okay, so in this video we learned how to plot some power of x, fractional power and integer power, and we saw how their behavior changes as you go from integer power to the fractional power. In the next video, we will learn how to plot family of ovals and family of spirals. So to know more, please see the next video. Thank you.